Well, friends, happy Monday morning. Made this video 3 days ago. Found out that when I had transferred all of my work things to my parents' house, that the gain on this camera microphone turned all the way down, and so that is why there was a non-working video. So here we are. I'm teaching the same lesson 2 days later. Hopefully I do it justice the second time. But if you wanted to know, I have set up shop in my parents' exercise room. So I don't even know what type of exercise equipment this is that the whiteboard's behind, but I have a standing desk set up on the treadmill and a mini studio set up over there on a chair next to the walking machine. So there you go. For your pleasure, the Wendell basement. And this, if you watch the videos out of order, sorry about that, because I ended up posting tomorrow's video as well, just in case some people needed to get a head start. So, anyway, they'll both be available to you now when the sound was working, because I was using my iPad. But basically, this is section 7.1, alright? And it's all about, really, velocities. Now, granted, there's some ideas that they want us to know, right? You guys know that from last semester, if we had a position graph, right, and we took its derivative, we would get velocity. And if we had the derivative of that, we'd get acceleration, right? And if we had the derivative of that, we'd get jerk, right? That means we know how to do integrals now. So if we went backwards from these things, we'd go backwards. Really, the one that they're most concerned about today, though, is just if you go backwards from velocity, you'll get to position. Alright, so that's actually this whole lesson I'm about to give you is really concerned with that idea. Now, I think it's a good idea. Here's the interval they give us. 0 to 5 of this crazy looking function. I started with the crazy one. We'll get a little bit less crazy. And they, first thing is they want to know, like, when it's moving left, when it's moving right, and when it's stopped. Alright, on this interval of 0 to 5. And that is, we just haven't done that, but we've done that already this year. We just haven't done it in a while. So let's make sure we know how to do that. So if I graph this really quick, if I plug in 0, that's 0 minus 0 plus 1 is 1, squared is 1, negative 8. So 0, negative 8 is where this thing starts. If I plug in 1, that'd be 1 minus, and then 1 plus 1 is 2. 2 squared is 4, 8 divided by 4 is 2. So I'd have 1 minus 2, which is negative 1. So this thing looks like it's skyrocketing really fast, is what this thing looks like. If I plug in 2, 2 plus 1 squared is 3. Or 2 plus 1 is 3, 3 squared is 9. So if I plug in 2, this is 4 minus 8 ninths. So 3 and 1 ninth. So right about there. And I mean, we can just assume this thing's going to go up from there, right? When we plug in 3, we're going to get 9 minus a half, I guess, right? 3 plus 1 is 4. 4 squared is 16. So 9 minus a half is 8 and a half, right? So this thing is just skyrocketing up there. And we'd stop at 5. So it's going to stop at 5, but I would even run out of room on my graph here. So when is this thing moving left, right, and stopped? Well, remember with velocity graphs, things are moving to the left when it's below the axis, right? So in this case, that would be from 0 to, who knows what that is, let's estimate. So we should probably use parentheses, right? From 0 to 1 point, we'll just say 1-ish. Without a calculator, I don't necessarily want to solve that right now, so we'll just say it's not at 1 because this was at 1, negative 1, but we'll say right there. Then it's going to the right whenever it's above, right? So this would be from 1.1-ish up to 5, just because that's our interval. And if we wanted to say stopped, honestly, if you put nowhere, I would take that, but usually the book would want right at 1.1-ish, or wherever that is, because that's where it's, instead of moving to the left, right, it stops and starts moving to the right. So it's just good for us to kind of review that a little bit. There's a couple questions on your homework that ask for that type of thing on a velocity graph. But now, basically, we've got a couple other questions that we're going to look at here. All right, so I'm going to go ahead and erase this and pose our other couple questions about this so we can answer those. And then we will kind of go a little bit broad about two definitions and try a few examples. This is one of those days I would have had you guys in groups if we were in class, but alas, we can't do that, so we will just do a couple together. But here is a couple questions. It says, suppose the initial position of the particle is that. So the first thing it's going to say is write not S of 0, sorry, the S of t equation, right? So this is actually what we would have done last chapter a little bit. We're going to go backwards and we're going to find C because we got a point to plug in. And then it's going to say, using this, it's going to say find the particle's position after 1 second. Right, so sometimes this might be asking for something like this. I want to make sure I'm not running out of room here. Not quite. We don't have a ton of room down there, but we should be all right. So this one is just such a good one because this one's actually kind of nasty to go backwards from, but it's good practice here. This is really easy to go backwards from, right? This is 1/3 t cubed. This is gross to go backwards from. What I might do, actually for just a second, I'm not going to go backwards yet. I'm just going to rewrite this. Can't we rewrite this like this? Is that okay for everybody? Right, I just brought that to the top. Now let's go backwards. So S of t will equal 1/3 t cubed. Right? And then we're going backwards. Backwards from -2 is -1. And we are allowed to do this without like q substitution or things like that because the derivative of t plus 1 is just 1. It's not like ugly or squareds in there or anything like that. But then we'd have to divide the -8 by the -1. But that's just a +8. And then we'd have to attach whatever the derivative of this to the bottom. But the derivative of this is 1, like we said. So that's just right there. And then we need our plus c. So everybody feeling good about that? Hope so. And then we got to plug in this. We got to plug in 0, 9. So if I plug in 9 over here and 0 right there, that's going to turn to 0. But this is going to be 0 plus 1 to the -1 plus c. So there we go. 1 goes to the bottom, but that's just that. So that's 8. So this is just 8. So if I minus 8 from both sides, I get c equals 1. So if I want to write the S of t equation, the position equation that we could graph, is 1/3 t cubed plus 8 t plus 1 to the -1 plus 1. Right? That's our equation right there. And we could graph that, and remember on a position graph, they don't ask for this in this lesson, so it's not a big deal, but position graph would be different about moving left and right, right? Position graph moves to the left when it's actually going down, and it moves to the right when it's actually going up, whereas velocity is what we said. It's moving to the left when it's in the negative, because that's a negative velocity, and it's moving to the right when it's in the positives, because that's a positive velocity. Now, we did all the hard work for this one, because if we want to find the particle's position after 1 second, what do we do with the 1 second? Boom, we just plug it in. So we'd have 1/3 times 1 cubed plus 8 times 1 plus 1 to the -1 plus 1. 1 cubed is 1, that's 1/3. Hopefully I'm still on the screen. I don't actually know. Barely. So sorry about that. Maybe I can move over here, I guess. 1/3 plus, and then 1 plus 1 is 2, but it's going to get sent to the bottom. So it's going to be 8 divided by 2, which is going to be 4 plus 1. This is 1 plus 4 plus 1/3. So 5 1/3. Which I think makes sense, right? Because if it's at 9 to start, so it's just starting at 9 on the number line, we know that it's moving in the left direction first. And it hasn't started going positive yet because it's just after 1 second. So it should have moved to the left. And if it starts at 9, then if it's at 5 1/3, it's moved to the left. Right? That makes sense to me. I'm feeling good about that. There we go. So that's a couple questions that you can answer about position. So then there's a couple other key ideas that we need to go over here before we do a couple examples. So let's see what we got. So, do you guys remember the words displacement and total distance? Well, actually, you may only remember the word displacement because we didn't really talk about total distance very much, but we have talked about something very similar to total distance. So we need to talk about the difference between these two, okay? I had one extra E here. And then the example that I used last time that I thought of off the top of my head is a good one. So I'm going to use it again. Do you guys remember when we were out? We were having a great time because we were actually in school and we got to go outside. We went outside of the track and didn't Brock kick the soccer ball, and I think Jolie climbed up to the top of the football bleachers and dropped a tennis ball. We're gonna do that again. So we're gonna say that Jolie is up here on the top of the. Oh, look at that hair. Oh, maybe that might be too much hair, Jolie. There we go. Sorry. There we go. But she's going to drop the tennis ball off the bleachers, okay? And the tennis ball went down, right? But let's just say we're at that point, we were only cared about what time it was, but I'm not going to kind of do that today. I'm just going to talk about these two ideas, displacement and total distance. So let's say that she dropped the tennis ball, and it dropped, and then it hit the ground, and then it bounced back up. And then right here, when it's like, I don't know, 7 feet off the ground, somebody jumps up and catches it. Who's got the ability to jump high? Well, Eli, you're tall, so we'll just say Eli catches it, okay? So Eli catches it down here, because he's tall. We're going to make a very tall person. With a long arm. Good job, Eli. So you catch it. So it's 7 feet off the ground, and we're going to say that's about 2 stories, right? It's 20 feet. So here's the difference between displacement and total distance, okay? If we say that this is how much the tennis ball traveled, right? It was dropped, it went down, it came back up. If we would say where is its like stopping position in comparison to its starting position, especially if it bounced straight back up, we would say that it's 13 feet away, right? So basically, if Jolie dropped it from 20 feet off the ground and Eli caught it 7 feet off the ground, the amount difference in height between where it was dropped from and where he caught it was 13 feet. And displacement, that's what displacement is. It's the change in distance, between the initial distance, or basically the initial position, I should probably say. The initial position and the final position. Right, that's really what that is, okay? And total distance, though, would be totally different, right? If we were to keep track of how far this tennis ball actually traveled, it did not travel 13 feet, because it traveled all the way down, and then it bounced back up and traveled this more. So the total distance would be 27 feet, right, total, because it went down and back up, right? So 27 feet. So total distance would be just basically how far as a distance, right, an object travels. Now, you might be like, okay, so why are these significant? What's the point? Well, you're going to have a lot of questions on your homework ask for these two things. And to be honest, what's awesome is if it says, what's the displacement on the interval, right? So the problem we just had an interval from 0 to 5. If it wanted displacement, we would just have to take the integral from 0 to 5, or wherever they told us, right, of our velocity function. Because velocity is going to go backwards to position, but if we actually plug in the two things and subtract them, that will actually be the change in distance. So displacement just ends up being kind of the straight integral. Now, total distance we'll talk about a little bit more when we actually do an example here. So we'll do one. And we'll kind of see how those end up different. But total distance is how far it travels, so it's actually kind of like total area, So what you might want to write down if you're kind of taking notes is that this is going to be like total area, and once you see that again, you'll be like, oh yeah, I remember how that's different. All right, so you're going to kind of see that. So we're going to do a couple different examples that you guys would have done in groups had you been here. I've got note cards for us, so let's see what we got. I'm going to start out with a simple one first, and then go to one that might make a little bit more sense to see the difference after that. So here we go. So in both these cases, we are finding displacement and total distance. So I'll draw the scenario and then I'll find them over here. So it'll probably give you a function. I would have given you a graph in class, but you can always sketch one or use your calculator. But this is actually just like a sideways parabola, like this. Okay, and then it actually gives you the interval from 0 to 4, so that's actually as far as it wants it, so that's why I did that. So, if we need to find the displacement on the interval, so both of these are going to be on the interval. Okay, so displacement and total distance. Alright. Just know that the problems that they're going to do, they're going to ask for it on the interval that they give you. Alright. So, if we want displacement, we just said that's actually how far it ends up away from where it was, is the area under the curve, because this is a velocity curve and it's going this direction, but the area under it would be how far it travels. So what we do is we're just going to take the integral of 0 to 4 of our function. Now we could int this, but I'm going to say it's probably going to be good to get some practice and not inting, but you can double check yourself with int if you want. That's no big deal. So I'm going to actually redo this and call this to the 1/2, right? So what's backwards from that? Whew. Well, we got to go up to 3/2, right? And then we also need to divide by that, but dividing by that's the same as multiplying by the reciprocal. And then we'd have to attach the derivative of this, but the derivative of this is -1, so we're going to have to divide by -1. So this is, sorry for the fact that we're so smushed together. Let me put this over here. So this is that, and then it equals this, but we got to still evaluate it from 0 to 4. So I'm not going to put the plus c on there, because we're just going to plug stuff in. Well, 4 is easy. If I plug 4 in, 4 minus 4 is 0, 0, that's just going to be 0. Minus. If I plug in 0, 4 minus 0 is 4. So I'm going to have a -2/3 times 4 to the 3/2. So that'll turn positive. Now, what's nice is 4 to the 3/2. That's a square root, so that's 2. And then 2 cubed is 8. So 8 times 2/3 would be 16/3, right? Or 5 1/3. So that is the displacement. So displacement, they didn't give us an initial position, right? In this one. The other one we had to find a plus c. In this, they don't even give us a plus c, right, to find. They don't want to know what its initial position was. They just want to know how much it changed from where it started to where it ended. And that is 5 1/3 basically spaces, right? Now here's what's interesting. Total distance in this case. This doesn't dip below the axis. So this thing is moving to which direction the whole time? It's moving to the right the whole time. Which means if it's moving to the right the whole time, it doesn't turn around, right? Like the tennis ball dropped and came back up. But this thing doesn't do that. It just goes one direction the whole time. That means the total distance is the same as displacement. But that's only if it goes the same direction the whole time. So we need to see one that doesn't do that. Alright, so that's what we're about to see. So let's see another one here. So we're going to do the same thing. I'm going to actually leave these two things up here so we can just kind of fill in our stuff here. But yeah, this one will be a little bit trickier based on what we have. So this one gives us v of t equals 3t minus t squared, and the graph, if I look at that, I could factor a t out and know that it's t and 3 minus t, so I know it's actually going to have intercepts here and here, but I actually do have a handy graph here. But it turns out that if we plugged in 1.5, 4.5 minus 2.25, this is going to be 2.25 right here. That's not a perfect graph, sorry about that. I probably should move this over to make it actually look more. That now looks stupid. well, sorry, you guys get the idea. So it's a parabola that turns around, does this, and then it's going to go down. So when it's at 4 and 5, I mean, it's going to be kind of way down here. So now this is where displacement and total distance are going to be different, right? Because displacement, we want to know how far it goes away from where it starts, which means the integral, oh, I forgot to write the integral down. Sorry, this is going to be from 0 to 5. So the interval that they give us is 0 to 5. And if we go ahead and calculate this integral, right, it's going to give us the fact that it moves forward and it moves backwards, but it's just going to be like, where is it compared to where it started, right? And it does all that work for us. We don't need to find a plus c because they don't even give us that information. They just want the displacement. But total distance, remember? You guys remember total area? Total area is where you had to find both of them, make them both positive, and add them together, right? Because it's kind of like that tennis ball that drops and comes back up. We want the whole thing, so we got to count this as positive and this as positive. So that's what we're going to do. So this is definitely the harder of them. And this will probably be the last example we do all the way through. Yep, I'm checking on our time here. Sorry if I got loud there for a minute. I had to go into the camera here. So here we go. Well, backwards from this, what's backwards from 3t? 3 over 2t squared, right? What's backwards from t squared minus 1/3 t cubed? Well, that's just gross. Good thing we only have to plug in 5, because when you plug in 0, you're going to get 0. So if we plug in 5, 5 squared is 25, and 25 times 3 is 75, so that'll be 75 over 2 minus, and then if you plug in 5 here, that's 125 over 3. And then if I was actually going to do these, I'd have to get a common denominator, so that's gross, but I'll do it, because this actually still isn't that bad, right? 3 times 75 is 225, isn't that right? $1.50, 225. So 225 over 6 minus 250 over 6 is negative 25 over 6. Or negative 4 1/6, right? So that means that this thing, wherever it starts, it goes positive for a while, but then it turns around and it goes back negative really fast, so it crosses by where it started, and it ends up 4 and 6 spaces that way from where it started, right? So that is the displacement. Now let's do total distance. Now total distance is where you've got to say, okay, it crosses right here, so I need to find the integral from 0 to 3 of this thing, and I need to find the integral from 3 to 5, and this one we're going to make positive, right? So I'm going to kind of put absolute value bars around it for right now. And then we're going to add those together. Now again, you can use int to double check yourself. I'm going to see how much room I got. I got a little bit of room down here. So I don't need to go through the work of taking the antiderivative again. I'll trust myself that it's right. But from 0 to 3. So again, I don't need to plug in the 0, but I plug in the 3. 3 squared is 9. 9 times 3 is 27 over 2 minus 3 cubed is 27 over 3, but 27 divided by 3 is 9. So I'm just going to make this over 2 and make this 18 over 2, right? So 27 minus 18 over 2 is 9 over 2, right? Is that right? Should be, I think, or 4.5. So that's the area of this thing, is 4.5. Now I've got to find the area of this thing, and it'll be negative. But then we're going to plug in or we're going to make it positive before we add it together. Sorry, I got lost in my train of thought. I was already plugging things in. So if I do 3 over 2 t squared minus 1/3 t cubed, and I plug in 3 and 5, here's a nice thing. I've actually already plugged in 5, and I got negative 4 1/6, or negative 25 1/6. So I'm just going to borrow my work, right? And I've already plugged in 3, and I got negative 4.5, but we're going to subtract it, right? Subtract. And I'm going to leave it as 9 over 2, so I can get a common denominator. So times 3 times 3, so negative 25 minus 27 over 6. What is that? Negative 40, negative 52 over 6. Is that right? And if I divide both of those by 2, it's negative 26 over 3. But I'm going to make it positive. So I make it positive. That's 26 over 3, and that's 8 2/3. Boom. And then I would add those together. So 4.5 plus 8 2/3. That's gross, but we can do it. That's 12. But then we're going to get even more than that because we got to do a half plus 2/3. So it's going to be 13. And take it times 2. So 4 times 3. So it's 7 6. So 13 1/6. Boom. Hopefully I didn't run out of room. If I ran out of room, I will tilt the camera down for a second. Can we see that? So 13 1/6. Now, again, that's going to be way easier with knit, but I would try to do a couple of them by hand at least. Right, and then you can see where you're at. Let me check the time that I've been going here. We're at about 26 minutes. So I think what I'm going to do is I won't write all of this out here for this next one, but I'll just try to pull this up and show you guys what's going on. This was the last one I was going to do with you guys anyway. So it's velocity, and it's from 0 to 2 pi of sine of 2t. Well, if you think about that, look at the wave there. Isn't there going to be a positive distance and a negative distance and a positive distance and a negative distance? Aren't those going to cancel out? I actually already know on this one that the displacement is going to be 0. You could go ahead and calculate if you want, right? You could take the integral from 0 to 2 pi of that function, and when you actually did that and plug stuff in, subtract it, you get 0, because this thing's going to end up right back where it started because it's got the same amount of positive and negative area. Now for total area, though, all of those would be counted as positive. So to be honest, I think that's the last thing I'll do on the board here. I'm not going to draw it all up, though. But if you guys wanted to do the total distance on this thing, I would not go through all the work of it. Right? I would say, oh, don't fall down. So this one was sine of 2t, right, from 0 to 2 pi. If I know that this thing makes some symmetrical shapes here, I'm not going to find this and find this and find this and find this and add them all together. I'm just going to find this one and take it times 4, right? And it just so happens I had this graph. This was at pi over 2. So I would find the integral from 0 to pi over 2 of this guy, and then take it times 4. Why don't we do this one to end really quick, just so we can have a trig one under our belt. Backwards from sine, it's negative cosine, right? Yeah, of 2t, and then we have to attach the derivative of the 2t, which is 2, but as a reciprocal, right, because we went backwards. So it's negative 1/2, and then from 0 to pi over 2. So if I plug in pi over 2, pi over 2 times 2 is pi. Cosine of pi is negative 1. So then I'm going to have negative 1 times negative 1/2, which is positive 1/2. And then I'm going to subtract whatever I get when I plug in 0. Cosine of 0 is 1. 1 times negative 1/2 is negative 1/2. Boom, add them together, get 1. So that would be the area of this, but if that's 1, this would turn to a positive 1, 1, 1. So my total distance would be 4. Right, and we already said that this displacement for this one was 0, if you wanted that on your notes as well. Alright, well hopefully the sound works on this one, because if it doesn't, I'm going to go crazy, but I turned the gain up, so we should be good. Alright, thank you guys for your patience. Hopefully not too many of you tried to watch the wrong video first, but I will be sending an email today about when we're taking homework questions on this thing. So I think that's what we got. Over and out, peeps.